A rapidly emerging PV technology is that of perovskite solar cells. Perovskites have seen a tremendous increase in initial efficiency in recent years. Perovskites are minerals with the general formula AbX3, where X is the anion, a negatively charged ion, and both A and B are cations, or positively charged ions. The figure illustrates the general cubic crystal structure of the perovskites AbX3. For photovoltaics, organic inorganic perovskites are used where the large cation A is organic, X is an halogen, and B usually contains lead or tin. The conventional device structure of a perovskite solar cell is the mesoporous cell structure, as shown here with its energy diagram. The perovskite absorber layer is sandwiched between a hole transport layer and an electron transport layer, generally titanium oxide nanoparticles in the mesoporous structure. The conduction band of the perovskite material is higher than that of the electron transport layer. Therefore, the light-excited electrons that diffuse to the perovskite titanium oxide interface are injected in the titanium oxide particles. We have seen a similar mechanism in the dye-sensitized solar cells. The electrons diffuse via the titanium oxide nanoparticles to the front electrode TCO. Similarly, holes are injected in the hole transport layer because of the relative valence band level. The challenges and potential solution for the perovskite PV technology, like the hysteresis effect, the use of lead and the degradation of the performance due to humidity, have been discussed in week 7 of PV2X. So we quickly went through the operation principles of the different PV technologies discussed in PV2X. Let's now look at their efficiency. This NREL chart shows the evolution of the best research cell efficiencies. The record efficiency of crystalline silicon has increased from about 14% in 1975 to a current record of 26.6% by Kaneka. The performance of CIGS and cadmium telluride solar cells is very similar, with a record efficiency of 22.6% for CIGS solar cells from ZSW and 22.1% for the cadmium telluride solar cells from First Solar. The performance of thin film silicon solar cells is lower, with a stabilized record efficiency of 14.0%. Of all technologies, the 3.5 technology results in the highest conversion efficiencies under both AM1.5 standard test conditions and concentrated sun conditions. The current record solar cell by Fraunhofer ISE has a conversion efficiency of 46%. Apart from the dye-sensitized solar cells, the organic PV research has only been going on for the last decade and a half. In that time, organic solar cells have reached a record efficiency of 11.5 by Hong Kong UST, and Sharp has reached a record efficiency of 11.9 for dye-sensitized solar cells. Perovskite solar cells have achieved an initial efficiency of over 22%, but not yet a stable efficiency. At the end of week 7 of PV2X, we discussed some concept for hybrid PV devices, in which different PV technologies are combined. We also discussed hybrid PV system, in which PV technology is combined with other technologies, for instance to generate fuel or the use of thermal energy. For the hybrid PV devices, we discussed various combinations, such as crystalline silicon with 3.5s, crystalline silicon with perovskites, and organic PV with thin film silicon. Regardless of the combination, there are 3 main configurations in which the technologies can be combined. In this figure, we see the monolithic integrated 2-terminal tandem device, which requires conductive tunnel recombination junctions between the different cells. This is a 4-terminal stack configuration, which needs an electrical insulator between the top and the bottom cell to operate. Another way of realizing a 4-terminal device is by using an optical filter. This filter redirects part of the spectrum to one cell and the other part to the other cell. The major advantages of a 4-terminal device are that the top and bottom cell are separated from each other. Therefore, there's no lattice matching constraint. The individual cells can be produced and optimized separately, and therefore is no need for current matching. However, this comes at the cost of the need for an extra junction box per module and more complicated installation. We also devoted some attention to the main measurement and processing techniques used in the PV technology field. For the measurement techniques, we looked at the effective minority carrier lifetime, which is a measure for the recombination rate and thereby the quality of the bulk material and how well the surface is passivated. We looked at a typical spectrometer setup that is capable of measuring the reflectance and transmittance spectrum of solar cells and materials. The absorptance can subsequently be calculated. We have defined the external quantum efficiency as the ratio between the collected charge carrier flux and the incident photoflux for each wavelength. By measuring the reflectivity of the solar cell, it can be transformed into the internal quantum efficiency. The short circuit current density of the solar cell can be determined accurately by multiplying the EQE with the solar spectrum and integrating over all wavelengths. A dark JV measurement can be used to characterize the diode parameters of a solar cell with a better accuracy than with an illuminated JV measurement. We have discussed the illuminated JV curve of a solar cell, for which the testing conditions such as the spectrum and light intensity have been standardized for obtaining reliable and comparable results. Finally, the processing techniques. For plasma-enhanced chemical vapor deposition, or PECVD, precursor gases are dissociated in a plasma. As a result of a fast switching electrode, a substrate in plasma undergoes cycles of electron and ion bombardment. The ion bombardment, as well as the diffusion of neutral gas particles in the plasma, leads to the growth of a thin film. PECVD is primarily used for thin film silicon alloys. Sputtering involves the evaporation of a target material through bombardment by heavy ions. Sputtering is primarily used for the deposition of TCOs, but can also be used for metallic layers and chalcogenides like CRGS and CZTS. During an evaporation deposition, the target material is evaporated through resistive heating or by electron beam evaporation. This type of deposition is used for the fabrication of metallic layers. Closed space sublimation involves thermal evaporation of a target material and a small temperature gradient between the target and the substrate to achieve deposition. Closed space sublimation is primarily used for the deposition of cadmium telluride. A chemical bath deposition involves placing the substrate in a solution containing the target material and is used for the growth of cadmium sulfide layers. Molecular beam epitaxy and metal organic chemical vapor deposition are epitaxial deposition techniques used for the deposition of 3,5 technologies like gallium arsenide. For MBE, pure elements are evaporated in infusion cells and a beam of these elements is then aimed at the substrate. A layer by layer deposition then takes place under high vacuum and high temperature conditions. In reference to MBA, MOCVD is cheaper, has a higher deposition rate and results in lower purity of the deposited alloy. For MOCVD, target atoms are bound to 3 hydrogen atoms or methyl groups and passed in gaseous form over a heated substrate. The elevated substrate temperature dissociates the precursor gas and a thin film of the target material grows on the substrate. Atomic layer deposition involves a series of sequential alternating flows of precursor gases that react with the substrate. ALD produces very uniform layers even at very small thicknesses, but is relatively slow. Finally, we discussed spin coating, which is used for organic PV. For spin coating, a solution is placed on a rotating substrate which spreads the solution out evenly over the substrate. The solvent then evaporates, resulting in a homogeneous film. That concludes the PV2X summary. I'd like to remind you that if some of the topics seem unfamiliar, we encourage you to return to the PV2X course and revisit those topics. I wish you good luck with the upcoming exams.